Hey guys, it's time for mean, standard deviation, variance. Alright, so first off, let's begin with the idea of average, which is the expected outcome in the sense of long term. You had a question earlier on the basketball games about what the mode would be. That's another expected outcome, the most frequent outcome. This expected outcome we refer to as mu, or the expectation of the random variable x, is what the long-term result should be. Now, the definition, therefore, is you add up the value of x in the support of x times f of x. And sometimes I write this way. Now, what this means is that it's talking about how things behave, but this average doesn't have to happen. First off, I want to show you how on test scores how you can calculate an average quite quickly without actually having to calculate anything if you treat this as an empirical distribution with equal likelihood. So each is 1/4, 1/4, 1/4. You add them up, you divide by 4. In reality, this is 1/4 of 85 plus 1/4 of 83 plus 1/4 of 95 plus 1/4 of 88. So using that each of these scores were equally likely, you were equally prepared. And this is exactly what you guys used to call the average. Here it's in the mean of an empirical distribution with equal likelihood. But I'd like you to point out that when things are equally likely, something neat happens. You can borrow 5 from here and put it there. Now we have 88, 90, 88. Let's take 2 from here, 88, 87. And you can see instantly that your average is very, very close to 87 2/3, 87 3/4 right in there. That's a nice little trick that some people use in calculating averages, but it's really in the area of averages with an equally likelihood outcome. It doesn't apply in any other place in probability in general. Now, what does it mean to use the formula for expectation to do this? Well, what it means is that I can do calculations that say, well, what is your expectation of your random variable if you threw away the average? What would you expect to have happened? Well, the average or the mean is the most likely event on the long run, so you shouldn't go above it and you shouldn't go below it in the long run. We should expect this to be 0. Well, expectation is a sum with the summation formula. I can do math inside of it. Now I can distribute it, or not really distributing the summation. This is actually commutativity of addition and subtraction, but you should write that out to convince yourself of this. And well, this is nothing more than mu minus mu times the sum of f of x, which is 1. Why, we do get 0. This is why we refer to the long-term average as the long-term expectation of nothing different than the average. We expect over the long term you're going to get the average. So in that hypergeometric one, when the teams were playing basketball, did you expect the mode, the most frequent occurrence, to be tie? I mean, that's almost impossible. Half the time you're not going to be tied. When you played 3 games, somebody's ahead. When you played 5 games, somebody's ahead in the wins and losses. So half the time you're definitely not equal. Interesting question. Now, what happens if we start applying this formula to things that we know? So let's begin with our hypergeometric. So our hypergeometric is the following. Probability is associated with an n, which is an n1 plus an n2. And it's associated with how many things you draw from that pile, right? Which is, well, you have n objects, choose n. This is without replacement, unordered, non-distinguishable. The things of characteristic 1, n, choose n of them, oops, x of them, how many can we get them, and then n2 of n minus x. Now this formula is not really nice to do something like this. To do that calculation. In fact, it's quite nasty. But thank God some people have worked hard and figured it out. What's really neat about this is that it has a nice answer. I'm not doing a choose here. I'm going to do divided by it. And this simply says, I expect to get the average of how many characteristic 1 I have times the number that I've drawn, which is a surprising answer, but it's a pretty nice answer. So it's a nice thing. You should memorize this. It's important to memorize it because I'm going to ask it. Now, those are the only two distributions we've worked with so far, one being uniform, like dice. So let's actually do a discrete distribution. I'm going to take the time to calculate the average of a discrete distribution. But I'm going to do it over some odd range. So I'm going to let f of x is going to be 1 over n. X is going to vary from some start plus 1, up to start plus n minus 1. In other words, it's a range of values. Doesn't have to be 1 to 5 or 1 to 12 or 1 to 20. But there are n values here. So first off, observe that when I've done it this way for a fixed s, that the sum of my f of x's will be n, 1 over n, which would be 1. So let's do the expectation of x. It is the sum from x equals s to s plus n minus 1 of x times 1 over n. Well, the 1 over n factors out. You were asked to kind of see if you remember that formula. So this is an interesting little formula. It's a sum of numbers. Now there's several ways you can do it. Let me write an example over here. This could be 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11. How would you add that up? Well, one way to do it is to put what's missing in front, calculate that, and then subtract what's missing in the front, because I think you have a formula for 1 up to n. That's one way to do it. There's another way to do it. There's an s everywhere in here quite a number of times. 1, 2, 3, actually n of it. I'm going to do it this way. There's n s's, and then it's 0 plus 1 plus 2 up to n minus 1. And so I just need to know this formula once. What is the sum of the numbers from 1 up to n minus 1? And why the answer is, drum roll, n plus 1 times n over 2. And so we get 1 over n times ns plus, that's n times n minus 1 over 2. s plus n minus 1 over 2. And there's our expected average. Now what's really interesting is if what we were doing from, say, the die from 1, 2, 3, 4, 5, 6, this would tell us that we know exactly what the sum is. Since s starts at 1, s is 1. Since there are 6 things, it's 5 minus 1 over 2 is 2.5, or the answer would be 3.5. And if you think of 1, 2, 3, 4, 5, 6, there's actually a balance point, 3.5, on a teeter-totter between those, which is another useful way to think of what a sum of this could be viewed as. It could be viewed as a balance point. All right. Now time for another slightly odd definition. And it's not meant on the face of it to be difficult, but it can be algebraically confusing sometimes. I am going to do the sum of x minus mu squared times f of x, which by definition would be the expectation of x minus mu squared. That's the function that's put in front of the f of x. I'm going to usually completely suppress the x in s here. Now, the reason I do this is that it turns out this is a very nice property, but first I'm going to demonstrate that this calculation can be done a couple of ways. One is I can actually, before I do the sum, square this out. And after I've squared that out, I can distribute the f of x. And now I can, quote, distribute the sum, which really means reorganize the sum. And lo and behold, this is the expectation of x squared. This is minus 2 mu times 1. Sorry, that's an x there. 2 mu times mu plus mu squared, why we get the expectation of x squared minus mu squared. So you don't have to do the complicated thing. You can just do the expectation of x squared. It's a little bit easier to calculate in general many times and do this. What is this thing? Well, we refer to it as the variance of x. Basically, it's somehow measuring the squares of how far something lands away from the average over all of the probabilities. And we call that the variance. Now, it's a kind of a befuddlement why we start with squaring it, because that gives a lot of credit to the things way away from the average. This number gets as big as it can when it's way away from the average, and then you square it, it makes it even bigger. But the probability of things way away from the average are frequently very small. But this is the idea called the variance. Now, we use the symbol sigma squared. Now, before I go on, I want to point out that mu is a Greek letter, sigma is a Greek letter. So in general, when I use Greek letters associated with the probability mass function or later on a continuous function, it is a theoretical average. It is a theoretical variance. So these are an indication of theory. Later on, when we do more descriptive statistics, we have x bar to indicate an average of empirical x's. We also use s for sigma and s squared. And these are empirical ideas associated with the same thing. That's the variance, and by the way, the square root of the variance, sigma, is called the standard deviation. Now, the surprising thing about these definitions is that sometimes they lead to very simple calculations. Other times they get quite complicated. I think you should look at two of the examples in the book. They did a uniform distribution, and the calculation is fairly straightforward. It's not hard. But the idea here is that if a formula is done in a simplified enough fashion, then you should be able to calculate it. So now I'm going to bring you back to one problem that I think you should be able to do. It is the uniform distribution. And the book absolutely loves to use M. So we're going to give uniform distribution on M of the first positive integers. So what we're going to work with is x is 1, 2, 3, up to m. That means f of x is always 1 over m. For this distribution, you should be able to calculate mu of that distribution and sigma of that distribution, or sigma squared of that distribution. They should be easily accessible to you. By the way, this one's formula is kind of nice. It's m squared minus 1 over 12. Why 12? Well, you need to discover it has a lot to do with a very simple formula that a young boy discovered long ago. Now, it turns out that the powers of the random variable are very useful to discuss because they're useful in certain calculations. So now we're going to talk about a moment. A moment is a power of the variable. And so when you do expectation of a power, that's a moment. You saw me calculate this earlier. And it becomes this, and this is referred to as the second moment of x. Now, the reason they're useful is that moments are associated with certain calculations. And so if you know the moments, then you know other pieces and descriptions of a formula. Now, there's another moment called the factorial moment. And that has its uses as well. And so they're extremely useful. Now, I'm going to go back to our hypergeometric model that we had. And I want to make it a teeny bit more complicated because the hypergeometric has this form that we have the function, but it's dependent upon a large number n and a characteristic n1 and the non-characteristic n1 and picking n things. Let's from here define a very simple number. So we've got this group, and here's all characteristic 1 and here's characteristic 2. So right off the bat, this n1 over n is the initial proportion of things of characteristic 1. And if we call that p, then n2 over n we can call q, and p plus q equals 1. And that kind of describes the situation as well, but it doesn't say how many things are in here. But the advantage of having a p and a q, p describing something happens and q describing not happening, or vice versa, is going to start playing a significant role in our models. And so this initial value of p, the probability of getting one right off the bat, is very useful. And so rewriting it with this new notation, the expectation for this PMF, which was n times n1 over n, simply becomes, whoops, that's a p, becomes np. The beauty of that is that it's a very, very nice way to do some calculating. Now, when you use these p's and q's, it turns out that frequently the standard deviation has a nice form. And so in this case, the standard deviation is an n, p, q, but it has an adjustment and has to do with this strange number here. But This I'm not going to make you memorize, but I do want you to notice that the proportions, the initial proportions we talked about, start coming to play in the problem. Now, since we have a definition of standard deviation and variance and average, and we have the empirical ones, what is common is that people extend those formulas to the empirical world and say, here they are. Well, x bar is exactly like mu. You add them all up and divide by n, or you take the probability of an occurrence times the x, it works exactly the same. However, it turns out that we need to do an adjustment for writing the empirical standard deviation. That's because the formula needs this strange little adjustment because it needs to predict something in the future that we're not there. So the S, which is associated with the S, which is associated with the sigma, has a slightly different formula, and that is S squared is the sum of all the xi's, because there are different xi's in your sample, minus your x bar squared, but you don't divide by n. You take this answer and you divide by n minus 1. Why? Well, we'll find out later. Okay. There is our introduction to mean, variance, and standard deviation.